In this video, we're going to look at mixing applications of differential equations. We're going to look at examples where rate in and rate out are same. These examples would turn out to be separable differential equations. When rate in and rate out are different, those examples turn out to be first order linear equations. We'll have another video for those examples. So let's look at the mixing applications. So start with rate of change. dy dt is the rate of change of amount of substance with respect to time. It could be sugar, salt, alcohol in the water, anything, any mixture we have. Rate of change would be equal to concentration in times rate in minus concentration out times rate out. Y of t would be the amount of substance in the container at any given time t. Amount of salt, amount of sugar, whatever solution we're looking at. Rate in and rate out is usually given in volume per time, which is liters per minute. Concentration of the liquid will be given in amount of substance per volume, which is kilograms per liter. Rate in, this is not rate in, this is rate in. Rate in times concentration in is liters per minute times kilograms per liter, which is kilograms per minute. Be careful with the units. You might have to do unit conversion. Let's look at the first example. A tank initially contains 40 pounds of salt in 600 gallons of water. So this is actually giving me my initial condition, 40 pounds of salt in 600 gallons of water. So when time t is 0, amount of salt is 40 pounds. Okay, at time t is equal to 0, water that contains half pound per gallon salt is poured at a rate of 4 gallons per minute. The mixture is drained at the same rate. Write the equation to describe the amount of salt at any time. What happens when time goes to infinity? What's going to be the concentration when time goes to infinity? How much salt will be in the tank when time goes to infinity? So let's start. dy dt is the rate of change, which is going to be rate in times concentration in minus rate out times concentration out. Okay, rate in, concentration in times rate out, concentration out. Concentration in. Okay, and y of t be the amount of salt at any time t. Is amount of salt, in this case this is salt, at any time t. Y of t is the amount of salt at any time t. Okay, so dy dt would be equal to rate in. At what rate are we pouring things in? We are pouring them at 4 gallons per minute times concentration in. We're putting 0.5 pounds per gallon minus the rate out is again 4 gallons per minute. We know it's getting out at the same rate. We don't know the concentration out. When it's heading out, how much salt is in the water at the time, we don't really know. So we can just call it y, because we said y is the amount of salt at any time t. So when it's leaving, amount of salt is y. And over the volume, when it's leaving, the volume is still 600 gallons, because we are putting the water in or the solution in at the same rate, and we're taking it out at the same rate. So we're now changing the volume. So this will turn out to be dy dt is dy dt would be 4 times 5, which is, no, this is 0.5. So 4 times 0.5 would be 2 minus y over 600. 2 minus y, 2 minus, that would be 2 minus y over, there's y 600 gallons times, 4 here, so that's 150. 2 minus y over 150. 2 minus y over 150. Okay, so now we can try to clean it up a little and express it as separable differential equation. That's going to be 300 minus y over 150. And dy dt is equal to 300 minus y. 300 minus y over 150. Okay, it is time to separate the variables. So I'm going to write it as dy over 300 minus y is equal to 1 over 150 dt. We are going to go ahead and take the integral on both sides. But in order for me to use a natural log, I need to have the derivative of denominator sitting on the top. So I'm multiplying, dividing with the -1. So it would be negative natural log of 300 minus y is equal to 1 over 150t plus c. Now I'm going to take the negative. My goal is to isolate the y, so I'm going to take the negative on the other side. Natural log of 300 minus y is equal to -1 over 150 plus a c. If I multiply c with the -1, it still remains a constant, so I'm just going to keep it as a plus c, constant c. Now we will raise both sides to the power e. So e raised to the power natural log of 300 minus y is equal to e raised to the power -150t plus c. Now, my amount of salt in the solution is never going to be negative. So I don't have to worry about the absolute value bars. It's never going to be negative. So e to the power c, I can call it another constant. So I can say e to the power natural log of 300 minus y would be just 300 minus y, and that's going to be e to the power -1 over 150t. All right, so this is my general solution for the differential equation. Now we were given the initial condition. Initial condition was, we were told that at the beginning there was some salt in there were 40 pounds. The initial condition was t is equal to 0 when y is 40. So when y is 40, 300 minus 40 is equal to a e to the power 0. So 270, 260. 260 is equal to a. So my solution from here, we can say y is equal to 300 minus 260 e to the power -1 over 150t. And that's my solution. That's my solution to the differential equation. And I can use this solution to find the amount of salt in the tank at any given time t. I can find, so this can be used to find amount of salt at any given time t. Amount of salt in the tank at any time t. Okay, so now, what if we were looking for concentration? What if we wanted to find out the concentration of the solution that's leaving the tank? Concentration is equal to amount of salt over the volume. Amount over volume. Amount of salt over the volume. So amount of salt is concentration at any time c. I'm going to represent concentration at any time c would be 300 minus 260 e to the power -1 over 150t divided by the volume. The volume of the tank was 600 gallon in the beginning. So that's going to be 600 gallon. So the units for salt are pounds, and this concentration would be pounds per gallon. And that's the concentration. What happens when t goes to infinity? How much amount of salt? What happens to y when t goes to infinity? If t goes to infinity, look at this function carefully. T e raised to the power negative, that means it's going to be in the denominator. When denominator becomes really, really large, this whole term will go to 0. And the y will be approximately equal to 300 pounds when t goes to infinity. 300 pounds. See one more example. A tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Okay, so when time is 0, y is 15. Pure water enters the tank at a rate of 10 liters per minute. Solution is kept thoroughly mixed and drains from the tank at the same rate. So same rate coming in, same rate going out. The rate is 10 liters per minute. All right, so rate of change dy dt is equal to rate in times concentration in minus rate out times concentration out. Okay, so rate in is at what rate? Rate in is 10 liters per minute. 10 liters per minute. 10 liter per 1 minute. Concentration is 0 minus the rate out. The rate out is also 10 liters per minute. And the concentration out, we don't really know. That would be y over the total volume. The volume is 1,000. All right, so now we are going to clean up this differential equation and go ahead and solve it. dy over dt is equal to, would be 0 minus, this is going to be cancelled, y over 100. Okay, so it turns out to be dy dt is equal to negative y over 100. Let's isolate the variables. Dy over y is equal to negative 1 over 100 dt. Time to integrate natural log of y is equal to negative 1 over 100 t plus c. Raise both sides to the power e. E raised to the power natural log of y is equal to e raised to the power 1 over 100 t plus c. All right, this is going to become a constant a, so this will leave me y is equal to e to the power negative 1 over 100 t, and I'm going to call e to the power c as constant a. Okay, e to the power c as constant a, actually plus minus e to the power constant c. E to the power plus minus e to the power c, I'm going to call it constant a, so I'm going to make the y positive. So I'm going to get rid of the absolute value because I use a plus minus on the other side. Now, we were given an initial condition. What was that? We were told when t is 0, y is 15. When t is 0, so use initial condition. When y is 15, when t is 0, e to the power 0. So this gives me a is equal to 15. My y, my particular solution for this equation turns out to be y is equal to, let's see, 1,000 liters of brine. So that was 10 liters. A is 15, so 15 e to the power negative 1 over 100 t. 15 e to the power negative 1 over 100 t. This is 100. Okay, negative 1 over 100. Now, this is our solution. We can use this to find the amount of salt at any given time t. This is our solution. We were looking for how much salt is in the tank after 20 minutes. So y of 20 would be, we can just do 15 e raised to the power negative 1 over 100 times 20, which turns out to be 15 over e to the power 1/5, and it's not negative, this is just a mark here. That would be the amount of salt, and what's going to be the units? It's going to be kilograms in this case. Kilograms. Okay, the units would be kilograms in this case. All right, so that's it, and these were the two examples where we were mixing applications of differential equations.